Okay, everyone, let me see if I can finish this lecture, and then you guys can take the rest of the time for working on the lab. Any questions about the lab? Any issues come up? Yeah. Okay, so last time I was talking about control theory. Is this making sense to everyone? Have you seen this stuff before? Sure. Yeah. So the idea of control theory is you have a controller. It's usually a computer, and it has some way of bending the physical world to its desires. You're controlling something in the physical world, and the goal is to make it reach a certain state as defined by the user. So. The earliest control systems were autopilots for boats and airplanes. It's used a lot in industrial manufacturing, robotics. Obviously, a lot of control systems in robotics for controlling every aspect of a robot because it's a physical thing. And nowadays, it's used a lot in power electronics to actively regulate power converters. And so that's the idea. So you have a controller. It has some kind of actuator, some kind. So it has an output. It's able to have an output to a plant. And then sometimes, if it's a closed loop, there's a feedback. Optionally, you can have the plant be instrumented or measurements taken in the plant and those sent back to the controller, right? And then you have another input on the controller for the set point. So the user specifies what state the controller should put the plant into and hold it there. And then the plant has another hidden input here for disturbances. So the question is, if I design it, let's say I design a controller for a drone and it works pretty well, but how do I know it's going to work in like on a windy day, right? Like you don't know. If you test it inside, it seems like it's work. It's hard to account for these disturbances. So that's the idea. So we have open loop control, which is where the controller is able to manipulate the plant, but it doesn't have that feedback from the plant. It doesn't have a sensor that comes back into the controller. And I mentioned that toasters usually work this way, which is why they never really work quite right. And then you can have closed loop controllers where you have some kind of a sensor in the plant, and then usually that comes back and it's you calculate an error value. So the sensors are used in combination with the set point. In this case, I'm doing a difference operation between them, but it can be more complex than this. But you take the set point and the sensor readings from the plant, and then the combination of those serves as the input to the controller, and then the controller sends a signal to the plant, right? So this feedback signal is usually called a process variable, and this is called a manipulated variable. Right? The manipulated variable is what the controller sets. Okay? Okay, so the problem is that the physical world is governed by differential equations and the physical world is continuous. And controllers are usually discrete because they're made with computers, right? So in order to test that your controller works, you need to have some kind of a model for both the plant and the controller that can then be simulated on a computer or analyzed somehow to know if it works, right? Or I guess you could just use trial and error on an actual plant, right? That's another option, right? But this lecture is talking about how to model these physical systems. So one way to do that is through linear time invariant systems, which is basically just a way to say, you have a linear ordinary differential equation. I don't think this applies to partial. This is only for ordinary. So an ordinary differential equation is where you only have one independent variable, which is usually time, right? Whereas a partial differential equation, you could have multiple independent variables in there. So generally, this is an ordinary differential equation with respect to time, and it's linear, which means that you can only multiply each state term or a derivative of a state term or an integral of a state term by a constant. So you can't take two state terms and multiply them together because that would make it nonlinear, right? Now you might say, well, what if I have a nonlinear system? Well, every system is nonlinear. So this whole idea of modeling things as a linear system is just an approximation for simplification. So I even mentioned like even simple things like resistors are not linear. The resistance of a resistor is actually changing depending on the temperature and how much current's flowing through it, but we usually just assume that resistors are linear. Same thing with springs. You usually assume a spring is linear, but a spring is not linear because if you stretch it out too far, it starts to do bizarre things, right? So this is just a simplification, right? Okay, so usually linear time invariant systems are represented as an ODE, just a straight up ODE, like you guys saw a lot of when you took calculus and differential equations, or they're often also shown in a Laplace domain, S domain, right? Or you can actually represent them as something called state space equations, which is actually just a matrix form of the regular differential equations, right? Time domain, right? The state space is the time domain, but it uses matrices instead, right? And then there's, for discrete systems, there is a Z domain. You guys ever heard of Z domain? So Z domain is the equivalent of S domain, but it's discrete. It's not continuous. And so, and you can also have a discretized form of state space as well, even though state space is technically continuous, right? But so here's the problem then. The problem is that your plant is going to be a continuous system and your controller is going to be a discrete system, and yet somehow you need to combine all this together, and to simulate it, hopefully to be able to tune your controller to make it robust against disturbances. That's the whole plan. Now in this class, the way this relates to this class is that what we want to do eventually is be able to represent the cube. We're going to try to have a cube that balances on one of its 6 points, right? Right? Or 6 points? Yeah. There's 6 points on a cube, right? Or four, yeah. 6 sides, 4 points, yeah. 4 vertices. Anyway, one of those 4, we want to be able to balance the cube on one of those 4 points, one of those 4 corners, right? So the problem is that we encountered is when we tried to do this already, and it failed quite miserably, because we don't have any way to know how to tune the controller to make it actually do that, right? So we have the cube, we have everything we need to make it work, but when we run the code on the cube, it just falls over. And so we don't know what's going on, right? We haven't figured this out. So the plan is if we can represent the cube as a LTI, then we can design a controller and simulate it, either in Python or simulate, however you want to simulate it. We can figure out how to make that work virtually, simulation, and then we can make it work physically, right? But right now we can't figure it out how it works. It's like we know it's possible because we've run other people's code and it works, but our code doesn't work because we haven't figured out how to model the cube, right? Okay, so right, so. Anyway, so LTI systems are usually written as a transfer function whenever you're composing them into some kind of a control system, right? So this part is kind of confusing because an ordinary differential equation is just an equation, right? So like, for example, you'll have, like in physics, you'll say the total force acting on an object is equal to all of the things that contribute to that force. So like an external force plus the friction plus the spring, it's just an equation that says you have to equalize these two things, right? And then you can do with that equation whatever you want, right? You can solve it however you need to solve it. But a transfer function is when you take that equation and you restructure it into a canonical form where it ends up being a ratio. I think it's always a ratio. All the ones I've seen are a ratio, right? It's a ratio between the output variable over the input variable, right? So in other words, a transfer function introduces this concept of an input and an output into a differential equation. That's what it's, but ultimately it's just a restructuring, an algebraic restructuring of a differential equation. So So for example, if you just take force equals mass times the second derivative of the position, which is acceleration. If you convert this in, so this is the, what did I say this was? Leibniz notation? Leibniz, right? So the derivative of, second derivative of position with respect to time, that would be in the s domain just s squared. So what's happening, well, actually that's not the whole story. What's happening is we're taking x, which is the position variable, the state, the positional state, and multiplying it by s squared, which stands for the second derivative of that state variable, right? And then, so you just have, you end up having this equation. Now, then it's like, okay, well, that's what force is, mass times acceleration. But if we're considering this situation where we're considering the force as an output and the position as an input, then we could we basically create this ratio, F over X. And then on the other side of the equation, we have ms squared, right? So this becomes the transfer function. And the advantage of transfer functions is that you can compose them. So you can take a transfer function and you can join it to another transfer function, and in order to get the overall top level transfer function, like this becomes a hierarchy, right? Or an abstraction. This becomes very computer sciencey at this point, because you take two transfer functions individually and you feed the output of one into the input of the other, and you can get the equivalent transfer function of the conjoined transfer functions by doing a convolution operation, which is simply just multiplying the transfer functions in the S domain. It's just a multiplication in the S domain, right? It doesn't look so pretty in the time domain, but in the S domain, it's very elegant, right? So if you have these two transfer functions, you just multiply them together, right? And it turns out that actually what this ends up being here is this is an open loop controller function, right? Because we have, this would be the controller, for instance, and this would be the plant, right? And so if you don't want to have a feedback signal coming back, that, like, so if you're designing a toaster, for instance, then it would just be, you just multiply these guys together. And you might say, well, okay, then what? What's the point of multiplying them? Well, the point is because you want to check to see if that whole system is stable. You want to hit it with an impulse response to see if it's inherently unstable. You want to know if it has bounded input, bounded output stability, meaning if you give it a bounded input signal, hopefully it has a bounded output. That still doesn't mean it's a good controller, but that's the baseline, achievement you have to have for a good control. So you don't want to have any control system that is unstable. The plant by itself could be unstable, right? But together, the combination of the two should make a stable system. Okay, so so I talked last night about how you figure out if a system is stable. There's multiple ways. You can do it mathematically by calculating the impulse response. You can find the poles, the transfer function poles. If all the transfer function poles, meaning the roots of the denominator, right? Basically the values of S. Remember, S is a complex, you guys know this, right? S is complex number because the Laplace is a frequency domain. So if the complex poles of the denominator, if the complex roots of the denominator are the poles, right? Because for some reason, if you get divided by zeros in that transfer function, that's a pole, right? So if the poles are all in the left-hand plane of the plot, right? Meaning horizontal is real and vertical is imaginary, right? In other words, if all the real parts of the poles are negative, then it's stable, right? Meaning that the output of the transfer function will never blow up, right? So that's another way. And then, but I think probably in the electrical engineering department here, they prefer to just use software to figure this out. They're not going to take a piece of paper out and solve this stuff. Too lazy, right? So what they do is they open up MATLAB, they go into Simulink. They love to drag those little pictograms into Simulink, drag and drop. They just love that. They're in love with that because they don't have to write any code. You just drag and drop little kindergarten pictures in there. And then they connect the wires and they just hit the simulate button and that'll do it. Now what's Simulink doing? Simulink is simulating the differential equations And to do that, you have to use a numerical integrator, a solver. So there's a solver as part of Simulink that is numerically going from S domain to time domain, right? Because you can't really simulate something in the, well, you can simulate something in the frequency domain, but then you're just looking at like the frequency response, right? You're looking at, a filter response, that kind of stuff. But if you actually want to look at, if you want to track a signal with respect to time, you have to go to time domain. And that's what Simulink does. It's a numerical integrator. It goes to the time domain, right? The other way to go to time domain is to take the inverse Laplace transform, which is basically impossible, except for very simple functions. Like you can't really sit down and do an inverse. It's usually not feasible to do you can't convert S domain back to T domain. That's basically impossible, right? You can do it for very simple things. I showed you an example of that. But generally speaking, you don't do that. You don't do you don't do a closed form conversion. You do a numerical integration, right? Where you just kind of step through time, right? Okay, so, let's see. So there's this thing called an impulse response. So this is the part that always confused me. So I understand the transfer function, right? The transfer function is telling you how an ODE changes a signal, right? And how does it change it? Well, it can change the phase, and it can change the amplitude. And it can change the amplitude differently at different frequencies when you send a sinusoid in it, right? So that's what a filter does, right? It attenuates certain frequency bands, and it puts gain on other frequency bands. You can do low-pass filters and high-pass filters and band-pass filters, right? So that's what a transfer function does. But the problem is how do you define the actual input? Like, where's the stimulus come? What's the stimulus to a transfer function? Because you have to do that in the S domain too. And that part is kind of confusing. So there's this thing called a Dirac delta. A Dirac delta is when in the S domain is a 1. Right? And a Dirac delta is an impulse. I've seen it sometimes described as an infinite amplitude at time 0 and 0 everywhere else. But other places it shows it as a 1 amplitude, 1. It goes up to 1 at 0. So it's defined as 1 at 0 and 0 everywhere else. So it's an infinitely small pulse, basically, right? Now, how do you reproduce the Dirac? You can't. In real life, you could never, there's no way to, I don't think that exists in nature, right? It's a purely mathematical concept, right? Because if you tried to make this with a battery or something, it just wouldn't, it can't instantaneously, like the slope here is infinity, right? Because it goes instantly from 0 to 1, and then it is negative infinity slope back to 0, right? But that's conceptually, that is an impulse that has an infinite amount of frequency bands in it, right? Likewise, the same thing is true for the step function. Now, the step function, you guys might say, well, we use step functions all the time. It's just a pulse width modulation. Yeah, not really, because a pulse, like on a clock on a computer or a pulse width, it's not an infinite slope when it goes from 0 to 1, right? So a true impulse has infinite positive slope from 0 to 1. So it's defined as 0 when its time is negative, and 1 otherwise. That's a step function. Now, a step function in the S domain is 1 over S, right? Now, you might say, wait, I thought you said that, I thought you said 1 over S is an integral in the S domain. Yeah, but it's also a step function, apparently, too, right? And so, if you want to test the response to your transfer function with a step, you just multiply it by 1 over S. That make sense? Right? Of course, that's then you'll get the mathematical description, right? But if you want to see if it's, then you have to find the, then the next step would be find the poles, right? If you want to do it in practice, you would, again, you'd put a step function into Simulink, you'd connect it to your transfer function, and you'd run the numerical simulator in Simulink. Okay? Make sense? Okay. Oh, by the way, I mentioned last time, I mentioned that if you don't want to use a step or an impulse, you might want to use a sinusoid input, right? Now, I actually just looked this up. I didn't know this until yesterday. I didn't know how to make a sinusoid in the S domain. But apparently you can do that too. In the S domain, a sinusoid is the frequency in radians per second, right? Which is just 2 pi times the hertz, right? So the frequency in radians per second divided by s squared plus radians per second squared. So you can actually, what?
Isn't that just the Laplace transform of cosine?
Yeah, and the cosine is slightly different. But yeah, that's the Laplace transform of sine. So, but anyway, but the point of this is that if you take that and you multiply it against your open loop transfer function, then you can find the poles and check for stability, or you can just, this is a simulation, right? Now this is an example of a simulation where it's not stable. Look what happens. It kind of blows up. It goes, So again, this would be equivalent to a cruise control on a car where you set your cruise control and it undershoots and then it overshoots and then it undershoots by more and then it overshoots by more and then it undershoots for more and then it overshoots even more and it keeps going and going. Obviously, it's not going to go to infinity because your car has limited, acceleration, but mathematically that would be conceptualized as a linear system of which, cars are not. It would be unbounded, unstable, right? Okay, so we talked a little bit about this, how you could do this mathematically. So one of the ways you could do an inverse Laplace transform is if you get it in this form 1 over s minus a, right? But again, that's a pretty simplistic form. But in this case, we had, I used this trick basically to decompose a single ratio. I remember I started out with a single ratio, right? Right. S over s plus 3 times s plus 2, right? So this is a single ratio of two polynomials of s, right? And my goal was to get it into a form that I could do the inverse Laplace transform, which is just 1 over s minus a. Well, they don't match, right? Those don't match. Those are two different forms of the equation. So in order to do that, I had to break this down into a sum of two terms that were in the form 1 over s minus a. Right? And so to do that, I used this trick where I could solve for two unknowns with only one equation, but that's only because the two poles were unique. And then that gave me the two eigenfunctions. And it turns out that this form of the Laplace function, or this Laplace function can be converted into the time domain as a sum of two exponentials, right? Which are called the eigenfunctions. And so what you end up with is you can then plot these and you get this, right? You get this curve that's obviously, converging on 0, so it's stable, right? It's not going to, it's bounded, right? It has a little bit of an overshoot here. It's right here. There's a little bit of an undershoot here. It goes negative, and then it kind of settles back to 0, right? Now, when I first looked at this, I was confused because I was like, wait a minute, where's the input now? Like, what's the input? Well, remember, the input is already baked into this. The input is the impulse, right? Because I did this for the combined, I took the impulse response, what I'm seeing is the response to the impulse here, right? I'm not seeing like an arbitrary, like I can't like put an arbitrary input in this. I'm limited to inputs that can be like from a fixed repertoire of inputs. I can do sinusoid, I could do step, I could do impulse, and those are the only three I know of, right? But that's what you're getting with that inverse Laplace transform is essentially the impulse response. And so I did it in MATLAB, and I did the same thing in MATLAB. I just went in, and I'm terrible at Simulink, but this is really easy to do. You just take two S-domain transfer functions and you plop them down. One was a step, which is 1 over s. The other one is whatever that one is that I made up, right? And then I connected them together and I hit go, and this is what I got. Right? Now you might say, wait, whoa, wait a minute, that doesn't match. That doesn't match that. Why does that not match that? Why does your mathematical one not match the numerical integration one? Well, that's because my mathematical one was the impulse. That's the step. So that's two different responses, right? That's why they're different. Okay, so then I also hit it with the sinusoid, and again, I did this in MATLAB, and you can see that it changed the phase and the amplitude. And then I thought, well, how about some real examples of this? So I just came up with this one yesterday too. I was real proud of myself. So I have this RC circuit, right? And the idea is that imagine you have this switch, right? And when you throw this switch, right? So assuming the capacitor starts out discharged, right? and you put this switch in the B position, and then you switch it to the A position, you're going to short this DC, well, it doesn't have to be DC, but it's V in, voltage in of T, right? Voltage in of T, you switch it on A, and this is going to put a step into it, basically, right? It's going to hit, so this will basically create like a physical representation of a step function by throwing this switch. And then I have a resistor and a capacitor here. So let's assume that I want to know the capacitor voltage is my output variable. So I'm going to just label this node. The node between the resistor and the capacitor is going to be my voltage out, right? And so, which makes sense, because what else would I use? That's ground, and that's just going to be VDD, right? So there's really only one thing to look at here, voltage-wise. So you just come up with the loop, right? So V out is going to be, whatever this is, V out is going to be whatever your input voltage is minus whatever drop that you got over that resistor, right? And so how do you know what the drop is? Well, you use Ohm's law. But the problem with Ohm's law here is that we don't know what the current is here, right? So to solve for the current, you just use the capacitor current equation, which says that it's the derivative of the voltage, right, multiplied by capacitance, right? So you take this and you substitute it into this resistor current, right? And then so basically you just work it out, you solve it, and you come up with a transfer function here, which is VO over VI. And you could put them in the S domain, which I did, and that ends up becoming 1 over 1 plus RCS, right? Now, when I first did this, I was like, what am I missing here? Because what I'm expecting to see is shown here. If I turn that switch on, it's going to charge that capacitor up, and what it should happen is that the slope of that line should decrease until it reaches whatever the input voltage is. It'll saturate the capacitor, right? Right? That's what I expect to see, but that is not going to give me that, because remember, this is one of the rare cases I can use an inverse Laplace. And what is the inverse Laplace of this? It's just an exponential, which means this is going to be unbounded, right? This is an exponential function, so I'm not going to get this from this. And I'm thinking, what the heck am I missing here? I don't understand this. This is definitely a bounded system, but yet I did the math that says it's unbounded. So what's going on? Well, it turns out I forgot to add the step. Remember, the step is 1 over S. You have to multiply the step in the Laplace with this in order to get, which is what I did here. So 1 over S times that. Now I have 1 over RCS squared plus S. And now, if I were to do the inverse Laplace, I would get this, which I didn't do because I didn't have enough time. But I assume if you do the inverse Laplace of this, you'll get exactly this plot, this red line. But again, didn't confirm that one yet. Okay, so so I talked about this physical system model, and this is boring, I know, but this is the example I use for the rest of the lecture. So the idea is you got a robot finger that's dragging a coin across the floor, and so this is a very simple physics equation because the floor is going to give you some friction. Friction is a resistive force that is a function of the velocity, right? Velocity of the coin is the first derivative of the position x, right? So if x is my, of the y, actually it's called y here, sorry, not x, y, right? Y is my position here, and u is my input. That's the robot's force that the robot's putting on it. So I want the robot to move the coin in a very controlled and regulated way in order to get it directly to that line, but I don't want it to go past the line, hopefully, right? I don't want it to overshoot the line. If it does overshoot the line, then it's got to come back, right? So that's my controller. So the governing equation, and this is in, by the way, don't get confused here. So this is, I'm going to use Newton notation here, where a derivative has a dot. And I don't even know how to represent an integral in Newton's format. But in Lagrange is when you put the little prime, right? And Leibniz is when you have the dx, dy over dx, right? Okay, so this would be u, right? So what is u? My input force. Minus by dot. B is the friction coefficient, and y dot is how fast that coin is moving, right? So that's going to resist. The robot puts in u. The friction is going to resist the robot. That's why I subtract this friction force. And then I set this equal to m double dot y. Why? Because that's just the overall force experienced by the coin. So when I add up all the contributing forces, it should equal the overall force, right? Now again, that equation is kind of useless without without doing something with it. So what I do with it is I convert it into a transfer function in the S domain where y is the position and u is the force. So now I have a plant model for this coin, right? Now again, the goal is to do this for the cube. Can you do this for a cube? If we had the intellectual wherewithal, we'd figure this out, but we're still working on it. We'll get it. But we want to do a cube. This is a coin. Same principle, right? Of course, the cubes has more degrees of freedom. It might be a multiple input, multiple output. This is one input, one output, right? So very simple. Okay, so anyway, that coin is unstable, technically, because if you put a step function in it, you're going to be applying a force that is that you're going to apply a constant force, right? And if you keep applying a constant force, it's just going to go into orbit, right? So, but if we we want to define a, I'll skip over this, another example of spring mass system. This is another example of a circuit. Okay, I talked about, okay, so let's talk a little bit how to control the coin then. So let's say I want to control that coin. Obviously, I need to use a closed loop. There's no way to have a robot push a coin with an open loop system, right? That's just impossible because the robot would have no way to know what the impact of its actions are, right, on the coin. So for that, I'm going to use a closed loop control. So I'm going to have a plant and a controller, right? And but I'm also going to have this feedback. So the question is, how do we construct a transfer function for this? Because remember, I told you that you can use a convolution if you have a serial connection of two transfer functions, but now we have a loop. Like, how's that work, right? How do you figure that out? Well, so the way you do it is you look at this variable YCL. This stands for the closed loop response, YCL. This is actually going to be the process variable from the plant, meaning that, remember, process variable is what you're reading from your sensor in the plant, right? And then this signal, which is unlabeled, is going to be the manipulated variable, right? So I'm going to manipulate this variable in order to achieve the desired process variable state, and that's going to be determined by this ref, which is my set point, right? And so and I'm going to use this subtractor here. So I'm going to take the reference, subtract it from the process variable directly, and use that as the input to my controller, which is just usually called the error signal, or the input, I guess, controller input, right? And then, so what I want to do is calculate the transfer function of this with respect to that. So in this system, even though I've got some unlabeled wires here, I want to calculate YCL over Ref, right? Because I'm going to conceptualize the set point as being the input and the process variable as being the output of the overall combined system, right? So you have to do some math here. So the YCL, which is this guy, is going to be, you have to take the open loop transfer function, which is inside this feedback loop. So that would be the controller transfer function times the plant transfer function, right? And then, this is the cool part, you treat this subtractor as a transfer function, right? Which is Ref minus CL. Now you might say, wait a second, you can't do subtraction in the S domain. That doesn't make any sense. Yeah, you can. It turns out you can. Subtraction is just cool, right? So you basically treat this as a closed loop transfer function, except you kind of just ignore the loop here, right? You just multiply these three guys together. But the problem with this is that it's not in the right form. We need to have YCL over RF, right? So basically you just have to use algebra at this point in order to get it in that form. It's just all algebraic stuff, right? So you can expand that, move that one term over to the left-hand side. You can factor out YCL there. And then you can divide both sides by 1 plus GP times GC. Okay, so far so good. I still don't have a ratio though, something's missing. So what's missing here is I've got two variables. I need to have both variables on one side of the equation in a ratio, right? So notice that RREF is over here on the right hand. I need to get RREF on the left-hand side. So you just divide both sides of the equation by that, and you get YCl over RREF equals GPGC over 1 plus GPGC, right? So that is the quintessential closed loop transfer function, right? So you can apply that same structure whenever you have a closed loop. Now keep in mind though that that closed loop may have more than two transfer functions in it, right? Also, this closed loop might actually be part of a bigger closed loop, right? It may be nested. You could have controllers nested inside of controllers, right? So for example, in a robot, you may have a closed loop to control one finger, which is contained inside another closed loop that controls the hand, which is inside another closed loop that controls the arm, which is inside another closed loop that controls the body, right? So all of this stuff can be very easily composed into complex systems, right? Just by applying the convolutions and the closed form formula and doing algebra to get things into the form you need. Okay, so the controllers, how do you build a controller? The simplest kind of controller is a PID controller. You guys already learned this when you took 274, but I don't think you learned this in the context of transfer functions and Laplace. I think you just kind of hacked it, right? Or use a ROS to do all this stuff for you. So how does a PID controller look inside the S domain? Well, it's basically, it looks like this. So you guys know you have a proportional, a derivative, and an integral tuning parameter, right? And then you have an error, right? So your error is your input, and then you have an output, right? So this is the transfer function of just the controller transfer function. What you're building is the controller by itself transfer function without being part of the closed loop yet. And then when you're done with this, then you incorporate in the closed loop, and then you hit it with an impulse, right? Or a step or whatever you want to hit it with. Okay, so the derivative is just S in the S domain. It's just multiplied by S, whatever the constant is, right? Now it has to be a constant if it's linear. And then the integral is just 1 over S, or S to the minus first power, right? So actually in the S domain, pretty simple to build a PID controller, right? You just have the proportional has no S, the derivative has constant coefficient times S, and the integral is constant coefficient times 1 over S, right? And then now the problem though is I mentioned that you don't want to have S to the minus 1 anywhere in your transfer function. That's a noob move. Like you don't, that's an amateur move. Your transfer function shouldn't have any exponent of S less than 0, right? So, but that's okay. You could just multiply it by S over S, right? To get that out. So what you end up here is transfer function is KD times S squared plus KPS plus KI. Notice the I doesn't have any S over minus 1 because we put that, we multiplied everything by S over S, right? Okay, and then the PI controller would be the same thing. Okay, so then the same thing without the derivative. And by the way, you guys remember what those things do, right? The idea is that you have an error, and then the derivative term is the idea of having the derivative in there is that as you start getting closer to the set point, if you want to slow down if you're approaching the set point too fast, basically, or if you're diverging from the set point too fast, you want to kick it into even higher gear to get it back, right? That's kind of the idea of the derivative term. And the integral term is about if you start spending a lot of time away from the set point, the more time you spend away from the set point, again, you want to give it extra kick, right, to get it there, right? So that's the idea of those two terms. And then of course the proportional is just saying, if you've got error, you got to kick it into whatever, plus or minus to get to your set point. Okay, so then if I have a PI controller, you can create an open loop transfer function, which is just that ratio I showed you multiplied by the plant model, right? So what is my plant model? Well, remember my plant model is, I don't know if you remember this, but this is the transfer function for the coin, right? So this is the coin. It was 1 over m. M was the mass of the coin. Over S times S plus B over M. B was the coefficient of friction of the whatever material I'm dragging the coin over. The robot's pushing the coin on, carpet or floor, right? Sandpaper, whatever. And then this was the transfer function of the PI controller. I dropped one of the terms to simplify this, right? This is not PID, this is just PI. Because it got too big. The whole PID controller was too much. So then I set, also I'm going to set mass to 1 and coefficient of friction to 1 just to simplify this a little bit more. And so I end up with this. And so I calculate my open loop transfer function, which is the product of those two, controller times plant, and then the closed loop transfer function. And this is why this starts to get complicated fast. The closed loop is the open loop over 1 plus the open loop. So I got to take the open loop transfer function and reproduce it twice. I have to copy and paste it twice into the closed loop transfer function. And then I have to get this back into just a simple ratio, right? Which, that's why the electrical engineers don't do this with paper. This is just too complicated, right? So anyway, I did it. It took a while. Okay, so then the question is, okay, then I've got that. But the problem is I have these variables in there. I've got the proportional and the integral control. How do I set them? Well, what a lot of people do, I think, is they do the random trial and error, which is retarded, frankly, right? Because we have a mathematical representation, right? In theory, we can find the optimal numbers for that, right? But how do you do it? Well, the way I did it, I came up with my own method, which is probably not a great way to do it. So I said, okay, what I want to do is I want to make sure the poles are negative, right? I want to basically engineer the poles. I want to put the poles of that transfer function where I want the poles to be. So in order to do that, I have to factor the denominator. The denominator is the key to the poles, right? Because you divide by 0, you get a pole. So if I have a polynomial, I got to factor that polynomial. And then once I have it factored, I can figure out where those poles are supposed to be. So how do you factor that? Well, it's a third-degree polynomial. You got to factor a third-degree polynomial. So I had to remember, because the last time I did this, I was like in 10th grade, I think. So s plus a plus s plus times s plus b times s plus c, right, will give me a third-degree polynomial of this form. And then the coefficients there is a plus b plus c times s squared, ab plus ac plus bc times s plus abc, right? This is just basic. Now you might say, well, now wait, you went from 2 unknown variables, now you got 5 unknown variables. You got a, b, and c you got to worry about now. Yeah, but well, what I did here was I said a plus b plus c is my coefficient for s squared, which over here is 1, right? So I know those have to add up to 1, right? And then the Kp has to be AB plus AC plus BC, and Ki has to be ABC, right? So what this allows me to do is I can pick whatever values I want for A, B, and C, and from those values, I can then figure out what Ki and Kp are for those, right? So that was the idea. Again, I think there's better ways to do this. So I just picked random numbers here for A, B, C, and I came up with these two Ki, Kp, and then I went back and I simulated that. So I substituted in my Ki and Kp back in the original closed loop transfer function. I put that in the Simulink, and I hit it with an impulse, and I could see that it is stable, but not great. Because, why is it not great? Because it kind of, remember the impulse is a stand-in for the set point, right? So what I'm really doing is, it's like I'm driving my cruise control, and I set my cruise control setting as an impulse. And then I want to see the corresponding process variable, which is the speed of the car. So what that basically means is that this yellow line is supposed to track the blue line as closely as possible, and it's not really doing that really well. I mean, it doesn't go to infinity, but it kind of goes up. It goes up and then it... Oh, by the way, notice that MATLAB, I don't know if you noticed this, but the impulse in MATLAB is infinite. It doesn't go to 1. I haven't worked that out yet. The Dirac delta, does it go to 1 but notice this one is just a huge impulse, but you can see that there is a kind of a delay and then an overshoot here, right? So it's not great. So what you want to do is clean that up a little bit. Oh, there's this. I also did it with the step. This is the step response. You can see it's not great. You can actually look, this time is correct. So that means that this guy is not going to reach the set point for 35 seconds. It's going to take 35 seconds for this to work, this controller. So, so I went ahead and just started, tweaking it now. So I increased the proportional and I increased the integral, and you get different responses. So I increased the proportional and it was faster. But it overshot, undershot, overshot, right? Then I increased the integral and it got worse. I don't know why. Yes?
So from my own proposal lab, there is an equation to find settling time from your transfer function. So why not set your settling time to an appropriate value and then work back from there?
Yeah, that's probably a better idea. Yeah, that's a better idea. So anyway, so that's basically it. So that's one type of controller. There's other ways to build controllers, and there's different ways to tune them. Now, the final thing I want to talk about is, and to me, this is the real problem, is that controller that I just designed cannot actually be built because there's no continuous computer to build that, unless you, like I said, if you could build it like as an expansion rate of steel, right? Like if you could create a piece of steel and convert the speed of the cars going to heat somehow, and then that heat causes the steel to expand, which then manipulates the accelerator of your car. That would be the only way to build that controller that I know of, right? If you want to build this with a computer, it has to be in the discrete, right? Now, though, in the discrete space, you introduce another parameter to this whole thing, and that's called the time step. It's how fast your computer is, basically, right? How fast does it recalculate the control law, right? How fast does it implement? And for that matter, by the way, even the control law, S-domain, you can't directly implement S-domain. You can just integrate it numerically, but then that's also going to be discrete. So for that reason, there's this thing called Z-domain. So Z-domain is the discrete, the equivalent of S-domain. And this is quite interesting. This is kind of cool. You have, notationally, it's a little different. They use square brackets instead of parentheses. So instead of x of t, they'll do x of n with n in brackets. Why brackets? Because it's no longer time, it's a sample number, right? And the other thing is that, and this is the part that kind of surprised me, if you take z and you raise it to a negative exponent, now remember I said you never do that with s. Whenever you have a transfer function, s never has a negative exponent, right? You always adjust it. But in the z domain, a negative exponent, when multiplied against the variable, represents something special. It means the sample from that variable n samples ago, where n is the inverse of the exponent. So for example, if you have z to the negative first power multiplied by x of z, right? Notice I went back to parentheses there. So brackets in the time domain, parentheses in the z domain, I think. But anyway, z minus 1 times x of z means whatever x was in the immediately preceding sample, one sample ago, right? Or you could say z minus 7 times x of z. is 7 samples in the past, right? Now, the reason this is significant is because this now makes it directly possible to implement this in C code. Because all you have to do is take your samples and put them in a shift register. And you can tap the shift register and you can get these values. Does it make sense? Can't do that with like a regular system. So, or S domain rather. But there are some other differences here. So a Z-domain equation is actually called a difference equation. It's not called a differential equation. The biggest problem with Z-domain is that no one really knows what the, well, I shouldn't say that. It's not that no one knows, but the stability criteria is a little vague. So with S-domain, it's very simple. If the poles of your S-domain transfer function are in the left plane, meaning have a negative real value, stable. But with Z-domain, it's not quite that straightforward. You can calculate poles of a Z-domain transfer function, but you can have poles in the right plane and it'll still be a stable system, but the settling time will depend on how close those poles are to the origin. So a system with poles close to z equals 0 will settle rapidly. A system with poles that are close to the unit circle around the origin will settle slowly. A system with poles right on the unit circle may have a sustained response, or it may have an ever-growing response, which means not stable. A system with poles outside the unit circle will definitely be unstable, and they'll grow exponentially. All right, exponential response. Okay, so what about derivatives and integrals then in the Z-domain? So if you have, integrals and, so this is the confusing thing. Integrals and derivatives don't really directly even apply to a discrete system. What you have here is something called a first difference that's kind of a stand-in for a derivative. So the idea is that if you have, the notion of a derivative in the Z-domain is z minus 1 over z, right? And you might say, what the heck does that mean? And of course, this would be multiplied against whatever variable you want to take the derivative of, right? But the reason why does this actually mean derivative is because if you expand this, it's actually 1 minus z to the negative first power, which means what you're doing is 1 means the current sample, and z to the negative 1 means the past sample. So if you take the difference between the current sample and the immediately preceding sample, well, that's the derivative, right? But it's the derivative in the discrete sense of the word, right? What about the integral? Well, this one, it took me a while to figure this one out. So you've got, the integral is z over z minus 1 times the variable that you're taking the integral of, right? But what does that mean? Why? Well, it turns out this is kind of cool. If you work this out, if you do some long division, if you take z minus 1 and you divide it into z, right? What happens there? Well, the quotient is 1, but you have a remainder, right? A remainder of 1. The remainder is the remainder, whatever the remainder contributes to this is the remainder divided by the dividend. The dividend. The divisor, sorry. 1 over z. Yeah, sorry. It's 1 over z, right? It's the remainder over the original, right? Is that right? Yeah, 1 over z, right? So this would be 1 plus 1 over z, right? I'm sorry, I had that wrong. I got it wrong. 1 plus 1 over z minus 1, right? That's why I was questioning myself. 1 plus 1 over z minus 1. So this is the remainder, right? Okay, so then if you take, now if we take z minus 1 and divide it into 1, you get the quotient is z to the minus first, but now the remainder is the remainder is z to the minus first power, right? So you have another remainder there. Okay? Make sense? And then if you take z minus 1 and you divide it into z to the negative first power, so again, if you expand this remainder out. So I expanded that remainder, and I get z to the negative 2 with a remainder of z to the negative 2, right? So then I keep doing this, and what ends up happening is you end up getting an infinite series of 1 plus z to the negative first plus z to the negative second plus z to the negative third infinitely, back to the beginning of time, which is basically the integral, right? You're basically adding up all the samples you've seen so far, right? Since the first sample, right? So that's where that comes from. Okay. All right. So the question here then is, I have a plant that's definitely continuous, and I have a controller that's definitely discrete. I have to design my controller in the S domain. I mean, I don't know how else you do it. But then if I want to implement my controller, I have to convert it to a discrete. I have to go S domain to Z domain. And then I have to figure out if that controller is stable. Because it might have been stable as a continuous system, but it may not be stable as a discrete system. So to do that, you have to do a conversion. Well, first of all, let's just kind of basically here. So here's the continuous system I had as an example before. So y plus sy minus 6 over sy. If you could just directly convert s to, remember, what is s? S is the derivative, right? But the derivative in the z domain is z minus 1 over z. And then s over 1 over s is the integral, and the integral in the z domain is z over z minus 1, right? So you could do that kind of thing. Let's see, so I did that, and I got, basically, this is the z domain representation of this S domain, right? So then you have to get a ratio, right? Why? Because I want to find the poles, right? I need to have a denominator I could find the roots of. So you end up, I ended up with this ratio after you work out your algebra, to reduce it into a form where I've got a ratio of two polynomials of z. So the denominator is z squared plus 3/4 z minus 1/4, and then I can factor that, and then I can find my roots. And the roots of the denominator is the poles. The poles is z equals minus 1 and z equals 1/4. So if this were S domain, that would definitely be an unstable system because of this 1/4, right? But in the Z domain, it's okay, because both of those are inside the unit circle. So stable, right? And by the way, it was also stable in the S domain, that one. Okay, but that's not really the right way to do it. The way you want to do it is you want to be able to incorporate a time step into that conversion. So the way that that's done is there's different ways to do it. One way is called the Tustin transform. And the idea with that is you can substitute 2 times z minus 1 over ts times z plus 1 wherever you see s in the continuous transfer function, right? And ts is the time step, which you have to pick, which may also be dependent on your hardware, right? So the question is essentially how fast can the ESP32 execute this control law, right? That would be your time step. So the idea there is if you have, what was the response? So this is, if you have the Tustin, so this is the step. So I've got the blue line here, which is the step. And then I have the response to my step, which was just this straight line. And then I did the Tustin transform of that transfer function. And you can see that with a time step of 1, by the way, ts is 1. So you can see every second that value of the discrete transfer function changes. and it's changing in a way where the way the Tustin transform works is it guarantees that the continuous version crosses midpoint between each two sample points, right? So this orange line is the discrete version of the transfer function you get with the yellow line. You guys with me? Okay, so all right, so let's just, the final thing I have is the example I had before, which is, so I have my robot coin thing, which is 1 over ms squared plus bs. That's my plant model. So I'm going to convert that to the z domain. Oh, yeah, sorry. So I set m and b both to 1. So I simplify it as 1 over s squared plus s. So this is the coin, right? This is the dragging the coin system. Then I can convert this to the z domain by substituting in the Tustin transform for the s's in here, right? So that gives me this. All right, so then I'm going to set the time step, which is this t, set that to 1 second. So I want the ESP32 is going to update the robot force every second, right? And so that allows me to basically, take out the t, and then I have to work this out to where I get a sensible transfer function, which is this, right? Okay, but when I say sensible, I mean it has I can easily find the poles, right? So I found the poles. I got a pull at 1 and a pull at 1/3. Is that stable or unstable? Well, that's unclear.
I mean, one of them's on the unit circle.
Yeah, the x, but the y, I said one of them's on the unit circle. Remember, the y is 0 because there's no imaginary part on these guys. But the 1/3, I don't know. It shouldn't be. I mean, the original S domain one wasn't stable, right? So this should be unstable. So now this is the part. Stick with me here. This part is I think is pretty neat. So to implement this in code. Okay, so let me just clarify. If you have an S domain, you can implement that in code. That's what MATLAB does. But it's running a numerical integrator, right? If I convert to the Z domain with the Tustin transform, I can implement this more directly in code. The way you do it is you have to basically, you have to put it into a form where the output, remember the output is y, right? And the input is u. If I put this into a form where y is calculated as a function of u simply by multiplying it by versions of z, right? Or actually, I can also include prior samples of y as well, the output. Does that make sense? If I can get it into that form, in other words, what I'm saying is you get it out of the transfer function form and you put it into another form where I calculate the current y as a function of z's multiplied by u's and z's multiplied by y's, like past outputs, right? Then I can implement it directly in code just using shift registers and multipliers and adders, right? So the way I did it is I pretty much had to work it out to where I got it into y of z equals 1/6 u of z. What does that mean? That means the current u, the current input, right? Plus 1/3 z minus 1 u of z. What does that mean? That's the 1/3 times the prior u, the prior sample of u, right? Multiplied by 1/6 z to the negative second times u of z. That's two u's ago. And then this is 1y ago. And this is one y ago. 2 y's ago, right? 2, right? Z to the negative second, right? So in other words, all I did was I took this and I recalculated as this. It's the same equation, but it's in a form where I can directly calculate the next y. Remember, this is actually keep in mind, this isn't the controller. This is what I'm doing here is simulating the coin, right? Because what is y? Y is the position, and u was the force that I put into it, right? So don't get confused. This is not, the controller would be calculating the force, right? This is calculating the position. This is creating a discrete form of the coin. But anyway, so the computer would simulate the position of the coin as a function of prior forces, right? And prior positions of the coin. That make sense? But in order to do that, I had to make sure that I didn't have any, I had to get rid of make sure that I didn't have any positive exponents of z in there, right? Because those would be the future samples. That would require knowing the future samples, right? You got to have negative or 0 exponents of z, and then the 0 exponent of z is the one that I have on the left side of the equation, meaning the current sample for y, right? So I can have the current sample of y here, the current sample of u here, and then prior samples of u and y here, right? Make sense? Now, what's cool about this is I never had to do an actual integral, right? Because if I had an integral, you would think I'd have to add up every value from back to time 0, right? But you don't. The way I got around it here is that you have access to the prior values of y. Prior values of y, right? Y is the position, right? So I was able to put this in a form where I didn't have to have a lot of memory. I only had to look back. I only had to have shift registers that took me back 2 samples into the past, right? And yet I was still able to execute a model of a physics model that had an integral in it, right? I think that's pretty cool. Anyway, so then I ran it in MATLAB. So this is the step response. Now remember, this is the response of the coin. Remember, the coin wasn't stable. If you put a constant force in the coin, which is the step, right, the coin just accelerates, right? But the point of this is to see how it looks, right? So I did that, and here's the z domain with time 1. You can see every second it tracks the coin, right, in a discrete way. And that's the S domain version, right? Okay, so now, last thing is, now I want to put the controller in there as well. So I've got my PI controller. I calculate the open loop transfer function. So now here's the problem. I don't know how to combine Z and S into one transfer function. So I had to convert the coin model into discrete, and I converted the controller into discrete. And then I calculated the open loop transfer function, and then eventually the closed loop transfer function. And I did all that. I put everything together. I simulated in MATLAB. And this is with a integral controller value of 1 and a proportional of 1. And then I simulated this, and you can see, what is this now? This is the closed loop transfer function, which means that this blue line is my set point. So what I'm telling the robot to do is I want you to move the coin 1 meter, right? And then I want to simulate it in a discrete way, and you can see that the robot is all in discrete. You can see it overshoots and then it comes down, but it's stable, but it's not performing really that well. But keep in mind, this is with a 1 second time step, right? And with, PID parameters are not necessarily all that good, right? Okay, but then I changed the integral, and that made things, I reduced the integral and it worked out a little better. And then I made the integral 0 and the proportional 1, and surprisingly, that actually gave me the best result. So this is just a P controller, not a PI controller. And then this is the P is 0.5.
Maybe a PD controller would be your best bet.
Yeah, I should have used D. I just didn't use it. Okay, so anyway, then, so I was going to cover state space, but I'll leave it at there because I'm out of time. So I did get through the whole lecture, but I didn't give you any time left to work on your labs, but at least we're done. Okay, so any questions about that? Okay, so there's only one more lecture I'm going to give, but not until after the lab is due, and it'll be on real-time systems. All right, and then we'll finish. We have one more lab after this, and we'll be done. Okay? All right, thank you.